Hello everyone and welcome to this presentation on the fundamentals of cross-validation. My name is Behzad Sabiti and I'm a member of Pattern Recognition Lab at Firdaus University of Mashhad. And today we'll explore the basics of cross-validation, a critical technique in machine learning for ensuring robust model evaluation. So let's dive in. Let's start with the basics. What is cross-validation? Cross-validation is a statistical method used to evaluate machine learning models by partitioning data into subsets. One subset is used for training the model and the other is used for validation. This process is repeated multiple times to ensure the model performs well on unseen data. The main purpose of cross-validation is to prevent overfitting, where a model learns the training data too well but fails on new data, and to ensure the model generalizes effectively. Now, you might wonder, why do we need cross-validation? The answer lies in the challenges of model evaluation. Without cross-validation, we often rely on a simple train-test split, where we divide the data into two parts, one for training and one for testing. However, this approach has limitations. For example, the performance metrics can vary significantly depending on how the data is split. This leads to high variance in results. Additionally, models can suffer from overfitting, where they memorize the training data but fail on new data, or underfitting, where they are too simple to capture the underlying patterns. Cross-validation addresses these issues by providing a more robust evaluation framework. To understand cross-validation better, let's discuss some key concepts. And the first is the bias-variance trade-off. And bias refers to errors due to overly simplistic assumptions in the model, while variance refers to errors due to the model's sensitivity to small fluctuations in the dataset. A good model balances both. Cross-validation helps us achieve this balance by ensuring the model generalizes well to unseen data. Generalization is the ability of a model to perform well on data it hasn't seen before, which is the ultimate goal of any machine learning project. Cross-validation comes in different flavors, each suited for a specific scenario. The most common method is k-fold cross-validation, where the data is split into k subsets, and the model is trained and validated k times. Another method is leave one out cross-validation, or LOOCV, where only one data point is used for validation and the rest are used for training. And this is useful for small datasets. For imbalanced datasets, we use a stratified k-fold, which preserves the class distribution in each fold. And for time series data, we use time series cross-validation, which respects the temporal order of the data. Each method has its strengths and weaknesses, which we'll explore in detail in the next part. To summarize, cross-validation is a powerful technique for evaluating machine learning models. It helps us address challenges like overfitting, underfitting, and high variance in performance metrics. By using methods like k-fold, LOOCV, and stratified k-fold, we can ensure our model generalizes well to unseen data. In the next part of this series, we'll dive deeper into techniques and implementation of cross-validation, including practical examples and code snippets. Thank you for listening, and I look forward to your questions.